Yeah, oops, let me see. Yeah. So, sorry for the delay. Welcome to lecture number 8 in parallel and distributed computing, summer 2024. Today we'll a little bit switch topic and go to an overview of what else we can do instead of MPI. So we'll touch several things and don't really go into a lot of depths today. Yeah, but it's more like seeing what else is possible. So we are talking about native C++ threads that enable us to do parallel computing just using usual C++. Then we look at a few things that we have to few problems that can arise here, race conditions and how to get around them. And then we look a little bit at your project and how it can be solved by other means than MPI. Yeah, so you remember your homework is to do it in MPI, but you can also do it in other ways. And this will do with both threads and with openMP. So that's what we are talking about today. So first thing is threads. So threads, yeah, see, I'm wearing an old t-shirt, there is a threads coming out, I noticed, yeah. A thread is a line of execution. So one thread is the spaghetti, yeah. So the code running from top to bottom, but you can have several of them in parallel. First, of course, threads. You can have many threads because you want to do multitasking, and old people like me who grown up with the idea that there's one processor in a computer. Yeah, so we also had back then. We also had threads, but one thread had to be paused while the other thread is executed. So this was called multi-threading, and now since we have many cores in our processors, we can actually run these things really in parallel. So the C++ standard library supports threads, so-called P threads, since C++ 11, which I believe is from 2011. I'm not completely sure how they named this, but I believe it's from 2011. If you use these things, so you have to compile your code with the option pthreads. Yeah. So very often in the example that we have later, this is taken care of by the makefile or by the CMake procedure. It already knows which code needs what option. So then usually users don't need to know this, but if you write your code yourself and compile it by hand, or if you write your makefile yourself, of course you have to specify that this option here is needed, pthreads. So what we also need here is the inclusion of the library threads, and then what you do is you define a thread, so it's part of the standard. By the way, everybody aware of what this means? STD column? Yeah? So it's a namespace, it's a standard namespace, yeah? So in the standard namespace, you will call the thread function that is generating a thread, and this thread function is given. This thread function is given a function as the first argument. So in C++, it's of course no problem to give functions as an argument. Yeah, let's see already. So and then you give the arguments to the function, to the thread function. Yeah, so this will call this function given these arguments that you add here. So this will start the execution of the thread, and then you want to know whether the thread has concluded its work. Yeah, so then you call join. And join is more or less a wait statement. So here your code will wait until the thread has concluded, yeah, and then the thread is closed. So this is, for example, if you, for example, the thread has something complicated to do, yeah, and you start your thread and then you terminate your program because it runs through, yeah. So because this is now separated from the main thread, yeah. So okay, what I want to say is this function immediately returns, obviously, yeah. Yeah, because there is a main thread and then you generate a new thread, right? So you'll have, if you generate one thread, then you have two threads, namely the main thread and the one that you have just started. And the main thread will go on and will probably reach the end, yeah? And when you don't want your program to be terminated right away, yeah, you have to wait for the thread that you started. And this you do by this join. So basically, this is the simple thing that we need to know. Okay, let's look at this very simple program. Okay, including IO stream, why not? Including the thread, of course. And then you need to have a function for your threads, and this function is of type void. So it will not return anything. Yeah. So usually you want to receive something from your threads. Now this you do the same way as you do it in MPI. Yeah. You pass an argument as a reference, so that the thread can write in this variable, yeah, instead of returning something, right? So, and this is now here just I mean, it's a stupid example. It's an counter, this is passed by reference, and this counter is incremented, I think, 100,000 times. Okay, so this is the function, and now we can call the same function several times, yeah, if we want to do things in parallel. So then down here we have an int counter, yeah, so this is an external thing, and then we generate the thread. We call the first one thread 1. We call it with the function increment. And then we have to hand in this counter here. And in order for the system to know that this is a reference, we have to generate a reference out of this. This is a little bit different from just putting the namespace, what is it called, the end operator in front of it. Yeah, here for the threads, they have to call standard generate a reference. So this is of course necessary for the variables that you want the thread to change. Yeah. So if you just give an argument that you can pass as a value, then you don't need to do this, right? So now you generate two of these threads. They do the counting, and then you join them, and it's a good style. It's not. I believe it's not necessary in this case, but it's a good style to test whether the thread is joinable. There's an additional safety mechanism that honestly I don't really understand myself what it's exactly doing, but so potentially when a thread has already been joined and you call join again, which would not happen in this case here, yeah, then this could lead to undefined behavior if you don't check whether it is joinable. Yeah, so it's better to do this, but it would work without it here. So, will this here work?
I have a question.
Please.
What if the thread isn't joinable yet? So
Then it will wait.
and it will wait. But
I mean, then it will.
that would just
Okay,
the
it's.
statement would not be true, and it would go to the next one, wouldn't it?
No, it's. Okay, I just said that I'm not. that I don't know the details about this. So, it's joinable. So, I believe that joinable means whether it is in principle, so that it has not yet. You know, joinable does not necessarily mean that it's joinable now. Yeah? Yeah, so that it will, when we call join, that this will go into a defined state. Yeah, in the defined state, if it's not yet, as long as it has not yet returned, it will wait in this point. So, okay, maybe I say something first. So, the interesting thing with these threads is that it's absolutely flexible and is also often used for things different than we do here with scientific computing, which often case looks similar to this thing, that we have the same function called twice because we'll have a big problem and we want to split this up, right? But often programs also have, software has different things to do, yeah? And these threads can be called with different functions, yeah, and can do completely different things, yeah. So this is maximally flexible, and for this reason, potentially not the go-to option when you do a usual parallel loops, for example. Okay, so having said this, now will this work? What is the problem with this? Anybody seeing any problem?
Maybe they are accessing the same variable at the same time.
Yes, so, right. So we've passed this here as a reference, and both these threads are working with the same thing, yeah? And this is something that we call a race condition. So, because these things run in parallel, it is undefined which one is doing what first, or in which order, or whatever, yeah? I mean, and also, for example, if your processor has only one core, yeah, it will schedule these somehow one after the other, yeah? So it's not necessarily parallel. Yeah, it may be parallel. Now, this, what you just described, is called a race condition. Yeah, so who is arriving first? Yeah, so you could imagine things like this. So, by the way, this is how old people like me learn programming. Do you know what this is? This is assembler. Yeah. Anybody ever programmed in assembler? Yeah. Okay, at least two. Yeah. So this is okay. So you know there's a register R. Yeah. And an external, so a variable in the main memory. So we load. This is how we actually do computation. The computer does computation, very down there. We load something in a register, and then we add 1 to this register, and then we store the register in the counter, for example. Yeah. So and now they. Now it's a little bit problematic in what order these things here are processed. Yeah, so you load something from the main memory. So the register would usually be local in the core. Yeah, and you load it, you add something, and then you write it back. In the meantime, somebody else loaded it in this register and writes it back later, so it will overwrite the first one. Yeah. So this is not good. So what do we do to prevent this from happening? Any ideas? So there's of course technology developed to counter this, and the first technology, and I guess also the oldest, is the mutex, which is short for mutual exclusion. Yeah, so this is also something that you can include with a library and call here using standard mutex MTX. So what is a mutex? A mutex, mutual exclusion, is a kind of a log. That's it's a log that you can just log, and when it's logged and somebody else tries to log the same log, it will be stopped here in this point. So this works like this. So there is a global variable, yeah, so maybe it's not the best style, but if you want to write a short program then you do it this way. So there's a global variable, the mutex, so all of them have access to the same thing, yeah. So and now it's the same code down here. Both of them are both threads are called to do this computation here. So the first one, let me see. So in this case, race condition no mutex. Why is there written no mutex between threads? I don't know. Okay, I don't know why I wrote this as a header here. So there is one thread and there's the other thread, and you see in time, so time is going down here, and the thread number 2 just so happened to come first, yeah, which is a little bit unusual because it was created later, but anyway, could happen. So thread number 2 logs this mutex because it appears here first. Then thread number 1 tries to log the same mutex, but since the mutex is already logged, it is stopped here. It cannot process, it cannot go on, so it's stopped. During that time, the second thread loads the counter, adds 1 and stores the counter, and then does the unlocking of the mutex. And once it is unlocked, the first thread can lock the mutex. Now the mutex is again locked immediately. The register is loaded, the register is added. During that time, if thread number 2 is trying to lock the mutex, it is stopped here, yeah, which I've not drawn here, but yeah, here's a stop sign for the thread number 2. So, and in this way, you can prevent these two threads from overwriting each other. Okay, so this is one possibility. It's not necessarily the most efficient one. And if you use multiple mutexes, you can get to a condition where you lock yourself in. Maybe we'll do an exercise to this, but not today. Okay, everything clear about mutexes now? It's not so difficult, but it's a little bit old-fashioned. What is a little bit more modern is to use atomic operations. So atomic operations is something that is implemented or supported on newer hardware. So back in the old days, obviously when the processor has one core, yeah, there was no necessity for atomic operations because this couldn't happen anyway. Yeah, but since we got more and more cores, the hardware has also evolved to avoid these race conditions by allowing these atomic operations. So an atomic operation is one that cannot be broken down. And for this, what you do is you take this variable that you want to, on which you want to have atomic operations, this you specify as an atomic. Yeah? So do you understand this nomenclature here? What this is? No, it's not vector. It's a template, right? Yeah. So there's an atomic template, and in this template, which is an atomic for an integer. Yeah. So an atomic integer, and we initialize it with 0. So now when I do this adding operation, any operation on this integer, like I'll count it up, then this will, by the hardware, yeah, so there's a hardware operation that takes care that this will be accessed only by one thread at a time. It's implemented in hardware. So if maybe your computer doesn't support it, I don't know, maybe either it will be simulated or it doesn't compile, I don't know, yeah? So these have been implemented in hardware because they're also faster than using mutexes. So mutex is a little bit old-fashioned thing. Atomics, so when I was in your age, there were no atomics, so I did not learn this. But there were mutexes. Okay, any questions to atomics? Yeah, so we are only, there's a lot of detail to this, but we are kind of flying a little bit overhead. Now I'll already reach the point where we look in, where I wanted to go to, the code. Okay. Am I in the right file? I guess so. So I hope all of you have already looked into your homework, yeah? At least seeing what we are supposed to do. And there, of course, you're supposed to do this simple simulation implemented with MPI. Yeah? And if you go to the Laplace 2D, which I put folder in Gaia examples, yeah, I guess you've already downloaded this, yeah, so I'll put it here too. There is, of course, here the MPI things, which I hope are empty, and then there's the serial version, and on top of this there are two other, and there's even a CUDA version. Unfortunately, we cannot run the CUDA version, yeah, on this cluster, but there's a CUDA version. There's also version for threads and also for openMP. Now, these codes are actually implemented and are already solving your homework, yeah, but in a different way than you are supposed to solve your homework, because you are supposed to do it with MPI. Now let's have just a look at this code for now the threads. Yeah, so we are just looking for the thread thing, and in this we have this library threads, and we have not used atomics and we've not used mutexes in this, so because they were not necessary. Okay, I hope you have already looked at this, so we'll go here a little bit, let me see. We have a void calculates time step, so this is not the function that we have to call. Yeah, there's the function that we have to call, right. So this is the function we need to call. So we call one time step, calculate one time step with the old data, new data. The mapper is the thing that transforms the two-dimensional grid in a one-dimensional array. Yeah. And yeah, so what else? The number of threads, the thread ID. Yeah, I believe we are using the thread ID size TI. Okay, I've not implemented this. I believe it's in the utilities. Yeah, size T is basically an integer. So in C++ you can generate your own data type, and this is what has been done here. So size T is an integer that my colleague just renamed this way. So, and now what we are doing is we are processing part of the nodes, yeah, part of the nodes, and we indicate this by I, and given our thread ID, we take a different part of the domain, right? So the thread ID is indicating what threads is doing this. So all of them are supposed to do different parts, right? So the zero thread, the thread number 0 starts from 0. The thread number 1 starts from num threads, the thread number 2 starts from twice num threads, and then we'll go through the inner grid size, which is just the right. So it's the right. So this it is starting from there in inner grid size. Okay, so it's I'm a little bit confused, but okay. So apparently the higher threads needs to have a larger size here, otherwise it would not work, right? Okay, sorry, I've not implemented this. Anyway, so the thing works like this. So we get our arguments and the command line arguments. So first we assume, so if there are no command line arguments, because you can start this with no command line arguments, so we'll have to specify what is the number of threads then, yeah, when you have no arguments. If you have arguments, so argc gives you the number of arguments to the command line arguments. So if it's 2, then you got command line arguments. And then you take the first one and set number of threads to the first one. So you just write, you know, the number of threads that you want on the command line. Constantly, what is in the 0 part? The 0 is the name of the function, I believe. Yeah, so because you always have, I mean, this is why we look for 2, yeah? So we'll always have 1, right? Okay. And then there is the rest that is already in the other code. So there's a timer, starting everything, old data, new data, initializing things, blah, blah, blah. So, and now comes the process of making threads. So we want to have many threads, yeah, multiple threads. So what we can do is we can use a vector of threads. So just generate them, we call them threads, and we give them the number of threads. So this will dynamically generate a vector with all the threads in it, but the threads have not yet been started. Okay, then we come to the main loop, and then we'll start from I equal to 0 till the number of threads. We'll start these threads. So assign to each of the threads a new thread called with calculation time step, and now we pass these arguments as generated references. So we generate a reference to the old data, a reference to the new data. Yeah, so instead of copying everything, yeah, so they all point in the same memory. Then we pass inner grid, entire grid, number of threads, and I. Yeah, these things here are passed by value. So they are started. Then, so this is a little bit modern style C++. I'm almost 47 next Monday, yeah. So I learned this in a different way, but here this is probably more like you would do it, for example, in Python, yeah. So you have your vector and you iterate over the vector. You don't even need to specify the the type, because nowadays you can use auto to just select the type that the thing has. So this will go over all of them. So take a thread as the it goes over threads, where this is how we call our vector, and now it calls each thread in the vector threads, and now it calls the join function for all of them. Notice here we did not ask for joinability, so we'll just do it this way. Okay, so and then we are basically done. Okay, and now we want to see whether this actually works. Where am I? So you can do the same thing. You'll copy the Laplace folder to your own folder. Don't mess around with my folder, please, or with the folders of your colleagues. So in order to compile all of this, what we do is we are using this tool CMake. And let me see whether I'm in the right space now. I think I have to go to build. I mistyped this. So in build, so we go, okay, so there was no build folder. So you generate a build folder. I don't know whether we have gone through this procedure already. Maybe we've already gone through this procedure, but I repeat it anyway. So you have the Laplace folder, and you don't want to compile everything in that folder, because if you want to redo it, you want to have everything that has been generated in one place. So this is why you generate a build folder, and then inside this build folder you call the CMake, but the CMake with the CMake file in the Laplace 2D folder. So this is why we need to have ... And now what it does, it generates the make file for all of these files, which include the serial version, the thread version, the openMP version, and potentially also the MPI versions. So, and now when we generated our make file, we'll call make to generate the things, and probably it does not a lot because I've already done this before. So now what we should see is that there is a bin folder now, and inside this bin folder there should be in Laplace 2D threads. So this is the one that we have been looking at. So now we can call these things threads. So okay, we'll do something else first. So there's a serial version. So this is let's look what happens when we run the serial version. So what we see here, it does a step, and it also gives out the speed at which it is processing, and this is called here MNUPS. This is million node updates per second, right? So, and what we see here is that we have roughly 400 million node updates per second when we run this thing in a serial code. And once this has terminated, how far is it going? I mean, I'm doing a bad thing here. I'm running it on the login node, but it's not.
In my case, it took 15 minutes.
15 minutes.
Yes, but I was using, of course, another computer. It was just one, and yeah.
Okay, so it says it took a minute. Yeah. So you see, this machine is 15 times faster than yours. Yeah, and hopefully this reflects here also this number here, which on average is 419 million updates per second. Okay, so this was the serial version. Now let's look at the thread version. So what happens if I run it without argument? Then obviously it will run with one thread. Let's just threads. Oh. Okay, I guess this will take 4 minutes. Yeah? I don't know whether we want to wait 4 minutes. I don't want to wait 4 minutes. Yeah, so, okay. What we see is that the thing comes with a certain overhead. Yeah? So the plain serial version was somehow faster. How many threads do we want to use? Give me a number. 4. Okay, let's do 4. So in order then to be at the same speed, right? Yeah. Oh. So annoying. I mean, this was my experience when I first, so 20 years ago, I wrote my first lattice Boltzmann solver, and then I thought I should parallelize it, and then I used threads and parallelized it, and it ran in parallel, but it was much, much slower than the serial version. And for the next 10 years, I forgot about parallelization. Okay, so back then I also used threads. Oh my God! Why not more? Well, it's not that much slower. It's
Almost.
Yeah. 71. Okay. Things can be pretty annoying. Things can be pretty annoying. So if you don't take care, you run into trouble. And sometimes trouble is also counterintuitive. And I find it a little bit counterintuitive in this case. So what we have to remind us is first what we are doing. Yeah? What exactly are we doing? And the other thing is, how does this fit onto our machine? Yeah? Because performance you get from fitting your program to your machine. So what we did is, maybe I'll just, why is this here? Okay, so see, we process so we are counting up I, yeah, so we go from left to right in our did I end up in the wrong? Why have I have this open twice? I don't know why. I'm a little bit confused now that I have opened it twice. PowerPoint Bildschirm. No. Okay, so that's supposed to be the right one. So we go in X direction first, yeah, because we said this is the fast direction, yeah, this is the fast. So here this is where data is consecutive in memory, yeah. So we let one thread go from left to right, and unfortunately, this doesn't seem to be the best idea. Now, in order to know what is the best idea, you should usually know what machine you are running on, which is annoying because probably your next machine looks different from your current machine, right? So it's always not very general. The machine we are using looks like this. So the Phoenix compute nodes, the ones we are on, they use two Xeon E5 something, each having 10 cores. And I've drawn it a little bit like it pretty strangely is. Yeah? So the thing looks more or less like this. There is a core, it's like in a sherry, so the core is a small thing. Yeah? And this core, these 10 cores, are connected to two caches, an L1 cache with 32 kilobytes at the core and an L2 cache at 256 kilobytes. And these caches are private to these cores. So the core up here cannot access the cache of the core down there, right? However, they all come together, these 10 together, share a bigger cache, the so-called L3 cache. So this is cache per processor of 25 megabytes. And then this processor is connected to two banks of memory, 8 gigabyte each. Yeah, and the same thing happens to the second processor. And this also means there are 32 gigabytes of memory in this compute node. But if the processor number 1 wants to access memory that is in the domain of the other processor, it goes through something that is called a quick path interconnect. Yeah, so they will, this is marketing. Yeah, so they tell you this is fast, and probably it's also fast, but it is of course slower than going the direct way. Yeah, so there is a bus that supports 9.6 gigabytes, giga transfers per second. To the other processor, which then again has to go through the bus to its memory. Yeah? So going this way is of course much slower than going that way. Now coming to our problem, or maybe coming to the solution. Okay, let's go back to the which I find a little bit counterintuitive still, even after thinking for this. So we'll have several possibilities. Here they are already implemented. So this is what we did now is that one thread is processing, gets one line in X direction and is processing these nodes one after the other. So it's actually in the quick direction. And the other way of doing it is going to skipping by the number of threads. Yeah, so this is basically the other way around. So all threads start in the same line. This is the idea, and then they process the next line. Yeah. So if I change this and save this, and I'll go back and run make. And then I go back to the what's it called, bin, and run it again. Then it's not extremely fast, but it is much faster than it was before, right? So I've used 10 threads. I don't know, you suggested 4. Let's see what happens. It's slower, yeah? So we have 20. We have 20 cores. Great. Okay. We have 20 cores. It's not, I don't know what is optimal. Try it with 8. The 8 is better than 20. Okay. Yeah, they are standing potentially they are standing in their own way. So the reason for this, or at least I hope so, I mean this is empirical observation, obviously, yeah, and you will, if you try to implement something in parallel, don't just trust it, yeah, so you need to do some empirical observation and you will potentially find these things counterintuitive, yeah. So the difference that we had here is that apparently this way, yeah, where the 0 thread takes the first argument, the first node, the 0 thread takes here 0 node, then the next takes its neighbor, and so on and so on. This is better than the first thread processing everything in its neighborhood and the second everything in its neighborhood. And the reason, which I believe, so the reason should be in the level 3 cache. Yeah? So you have to remember all of these threads are started in parallel. Yeah? So they all potentially, or in the optimal case, say, yeah, they will start from the same place. So they now read one cache line, and the cache line is now distributed over all threads. All threads access the same cache line. Yeah? Whereas when you you do it like this, that each thread gets a block of memory to process, yeah, which you could think should be optimal because it's optimal for that one thread, should be optimal for that one thread, right? But it's not optimal when you run several threads on the same processor at the same time, yeah, because it has to read many cache lines at the same time. Yeah, because now for each, so in this case, there's one line in the memory can be used for all the threads, where here all the threads needs their own lines of memory. So they have to read more lines at the same time, and this will slow them down. Yeah? And very often in these cases, reading memory is much more expensive than doing the computation. Okay, so please.
Could it also be that the join is slowing down
The join can also slow down, yeah.
It was just
Yeah.
that there was a join before or after the step calculation. So if we have more threads, it should wait. For example, if we have 20, we would have to wait 20 or 19, I guess, right? Or it doesn't work that way.
So in principle, okay, joining the threads is a bottleneck. Yeah, so this can slow it. I mean, this can of course also slow it down. So, for example, but I don't think that this is the reason here. I mean, otherwise, because joining the threads, I mean, of course, this is the place where it waits. Yeah, in so far, yeah, this is the problem, but it's not the reason. Because they have to be joined anyway, whether they work this way or that way.
Okay.
Yeah. Okay. So far with the threads. Now coming to something that is a little bit of higher significance than that for parallel programming. So again, with threads, these kinds of threads are not so much used in data parallel programming, say, yeah, but they are, of course, if you develop applications that have different tasks to do, yeah, so where things run concurrently, then pthreads is your way to go. Yeah? So, but if you want to do the same thing again and again, then probably your life is much easier using openMP. Now, openMP sounds a little bit like MPI, but should not be confused with it, yeah, because the philosophy is here completely different. We know that MPI is a message passing. Is message passing interface, yeah, that is particularly designed for distributed memory computers, yeah, and openMP is for shared memory. So this is something that you would use inside one machine, which again you are actually now using. Yeah, so we ask you to write an MPI inside one machine, which of course is possible, but not necessarily the best idea. Yeah, so inside one machine, the better idea is to use openMP because you are in a shared memory. Okay. So openMP is also since long ago. It allows you to write multi-threaded programs, and if you compile it, you have to use the option fopenmp. Otherwise, funny thing, it will compile, but it will not do something. So the code that is meant to run in parallel is marked with a compiler directive. Yeah, actually, so there are openMP functions, but the simplest functionality, and this is the only one that we'll use today, is that you can parallelize loops. And the funny thing is, you are just using the usual C++ style. So if there is no openMP, your program will run the same way as usual in serial. Yeah. So, but what you do is you tell your compiler that you would like to have a certain loop to be run in parallel. So of course you may have to make sure that your loop can run in parallel. You know, it's not dependent on its outcome later. So, and here it is also important for this to work properly. We have to specify an environment variable. Yeah, we come to this in a minute. Okay, so the example from our code. Let us see what is the code. Okay, as I said, there is in the SRC, in the source, there is an openMP version, which I may do. Did I already open it? I don't know. Okay, so this is the openMP version. In here, and this is very simple. Say, there is no header and no library loaded for this. There are openMP functions that when you want to use them, you also need a header. Yeah, but for the loop, you don't need this. So all you do inside the code, is to specify that there is this loop that you want to run in parallel. So pragma parallel 4. Now there is a few things that we specify, namely that that the variables in this loop are by default shared, but we specify that x and y are private. Yeah. So what does it mean, shared and private?
They can access inside, or I don't know in this case, but in terms of classes that they can access the functions.
Yeah. So it's a little okay. Good that I asked. It's a little bit different from that. So private. So okay. In MPI, you have learned that all the variables that you have are local. Yeah, because it is a distributed memory system. Yeah, so you have your own memory and somebody else has their own memory. So the entire program is run on different machines, yeah, at the same time, and all of them has their own copies of things. And if you want to communicate something, you have to send it. Yeah, here it's different. You're in one memory. Yeah, so this means when you access when your loop accesses a variable, then several threads access this variable at the same time. Now, either you want that or you don't want that, right? So you can specify whether a particular variable is the same for all of the threads or is private to the thread, such that it has its own version of it, right? So, and this is by default. By default, they are shared. Means by default, if we don't tell them anything else, they will assume that one variable exists only once. Yeah? So all of them accessing the same. But, of course, here we want to compute our positions. Yeah? And the position is, of course, different for the different threads. Yeah? Otherwise, they would all work on the same. node. And so this we specify by saying that X and Y are private. X and Y are private. And by the way, the okay. You know, I try to put this to don't disturb me, and anyway it comes through. Sorry. I was just disturbed. What did I say? So we were in private. Sorry for getting disturbed. Yeah, no. What I wanted to say is the I, yeah. So the iterator that we specify here, this is always taken to be private, even if we do not specify it as private. Yeah. Okay, let me see whether we have anything still to be said here. So this tells openMP to share variables, private, loop index is private by default, where it's declared, outside. So everything that is outside, outside the scope of this function, yeah, is shared. Or outside the scope of the loop. So, do we want to run it? We've already compiled it. And the CMake file and the make file have taken care of putting the right argument, yeah, so this f openMP argument. Now let us run it. By the way, how do we specify? So the main here is not taking any argument, so we are not specifying the number of threads here. Yeah, we have to export. Let's see. Okay. This is the number. The number is. It's a bit faster. It's erratic, huh? Sometimes it's fast, sometimes it's slow. Strange. Because we are. It's faster than that. Yeah, but the other thing. Okay, but yeah, this is not. I think it was not important now. Yeah. The only thing. Okay, we'll can do this in the exercise, but it's not essential now. I was hoping. You see, we are waiting for some time. Okay. Yeah, so average is low again. So the thing that is of course of importance, and I have to look this up, is what is this environment variable num threads. Oh, Konstantin, how can I display the value of this? Dollar sign? Okay. So, it's nothing. Oh, maybe that's the reason. Okay, so this has not been specified. Okay, so that's so we have to specify the number of threads that we want. equal to, okay, so what happens if we put it to 1? I don't know. So I guess it is kind of slow, right? If we put it to, yeah, let's put it to 10. What is it doing if we do not specify it? I don't know. I mean, at least it's a little bit more stable than if we do not specify it, right?
Probably it uses all of them. Or some.
Yeah, that would make sense, but I don't know. So it's kind of 800, yeah? So in improvements. Okay, any question regarding openMP so far? So this is the most easy thing to do, yeah? You just add one line, yeah, and it does your thing here in parallel. Okay, so there is one question that that already has come up about this ParaView thing. Or have you all been successful downloading and installing ParaView? Some nodding, some shaking head. Yeah, okay. So here you can download the thing, and so this is required to look at the simulation result. Yeah. So in addition to see the performance, so in how fast it is running, you have to make sure that you also get the right result, obviously, yeah, and therefore you have to look at your result, and this requires a software, yeah, which is a little bit a big software, in that sense a little bit annoying because you have to download and install it, and just to look at one picture. Because it's a powerful software that is an industry standard to, please.
If I'm gonna do like the project without using the code that you provided, I'm doing like from zero. I can't use the software, right? Because
Yeah, so then you don't know whether your result is correct. But you can also copy that part that is doing the output into your code. What about that?
Yeah, it should be fine.
Yeah.
But I also could make like a Python script, for example.
Yeah.
Because I imagine what the thing is doing is getting every pixel value and
Yeah.
assigning like a color for it.
Yes.
So it should be quite easy to do that, like with just a script.
Yeah, but your script could also be wrong.
But it's quite hard to get it wrong, I guess. It's just like printing an image with.
Yeah, but so I mean the idea. So okay, you write your own simulation software. Do you have any interest in looking at the results?
Yeah, of course.
So how are you looking at your result?
Right now it's just like printing the matrix on the.
Printing the matrix.
Yeah.
Can you read the
for,
matrix?
It's not gonna work for like 500, but like for testing it's
I mean the thing is supposed to be highly resolved. Okay, I mean, yes, the first time I did this, I was also printing the matrix, I agree. But it did not take long to notice that this doesn't work very well. Yeah, I mean, you can also write in a file writer. This is not extremely complicated, yeah, you can go to the ParaView documentation. Then they will tell you there are different file formats, and one of the file formats is just a list with the coordinates. No, it's not the coordinates. What is the simplest one? I think it's just rows, right? Yeah. So this is a header file. There's a header in the file where you get the size of the matrix, and then you write the values, and then you can open this in ParaView again and see the result. But the file format that has been used by the example code is a little bit more complicated file format, I believe. Yeah. But there is also the legacy standard 30-year-old file format in actually even ASCII, yeah, that ParaView can also read. I believe still can read. Yeah.
But I can just like disciple the part of the code that converts the matrix to.
Yeah, you can also use the thing that is already provided. So, okay. What again is annoying is, you see, we are accessing Phoenix only via this console, right? So if you want to display something, yeah, so then for the guys who are paying for working on Phoenix, there are dedicated nodes for displaying something. They are the ones with the big memory, because displaying stuff is more expensive in regard of memory than doing the computation. How big is the memory of such a node? 512 gigabytes. Yeah. So, and Konstantin usually uses 4 of them and together to get one picture, right? Yeah. So, you need what is this then? Yeah. You need 2 terabytes of memory to display some simulations. Not unusual. Yeah. So this is something that ParaView can do, because the name indicates parallel visualization software. So this can run on the distributed system itself, and can also read from distributed file systems. So where you also have where you distribute your results on different files and connect them together to get one picture. This is what we do when we do serious parallel computation. So unfortunately, you don't pay, so you have to do it the other way around. You have to download the stuff that you generated from Phoenix to your own computer and look at it at your own computer. Yeah? So you can either do it here, or you would do it in your own computer. And for this, if you are on Windows, what you would use is WinSCP. Of course, if you use Linux, then SCP, so secure copy, standard. So you'll take the same. So we are on this Phoenix computer, and we have this username. This is the same account that we are using here. So I guess this will be on YouTube. What is not on YouTube is the password, I hope. So you know the password. And now in this, I don't know whether I have to cut this out. Yeah, so we are in Laplace, we'll have this build, I've mistyped this build, and in bin we run it, and then there is this temp output INP. Yeah? So this is something that you have to that you have to copy. I'm not familiar with the software, unfortunately. So you have to copy this thing, and then when you have copied it, you can look at this in ParaView. So this is the software that you have to install, and then very basically you go to File, open the file, and then you will already see the result. Yeah. Now since where did I write? So I put it in my folder here. Then you have to decide how to what reader you're using. I'm not sure whether they make any difference. I'll take the first one. Then once you open, you still have to press apply. So, yeah, you are laughing, but wait, yeah? So, the thing is, if you are dealing with terabytes of data, you don't want your software to just process everything without being taught so, yeah? So, because this is a big problem. That most of the software, when you open a file, what it does is to try to read the file, yeah? And if your file is terabytes, you don't want your software to read the file. Okay, let's press apply, and then it comes, yeah? So, and actually this is, looking at this is now more or less all that we want to do. There's of course now all sorts of things, so you can, for example, play some fun. You can get some contours, yeah, so heat contours, yeah, you can process this and look at these results. Okay, get these. Have any more questions to ParaView or yeah?
Instead of ParaView, could we use Nuplot?
Can Knuplot open this file? Probably it can. I don't know.
You have, well, I created another one, the text file, or I created my function that creates a file that can be written with Nuplot, but it's just asking if ParaView is a part of the assignment, so we have to use ParaView.
Well, it's not part of the assignment. It's making comparison easier. Yeah. So I mean, you're supposed to show your result, and if this looks this way here, like okay, you can turn on here the eye. You can turn on and off. So if it looks like this in Knuplot, then you can use Knuplot.
Okay.
Yeah.
The problem, the function for writing the file is always implemented. You need only install ParaView and visualize. You don't need to implement this function for writing the file. What is the problem? And for Knuplot, you need to implement this. I don't understand your perspective.
Downloading ParaView is much easier. Implementing the function.
I mean, yeah, using ParaView. So we are not doing a lot with ParaView, yeah. But learning to use ParaView is also not necessarily a bad idea, especially for you, because you have to use it in another case, yeah. So, but anyway, yeah. Okay, I'll go to stop the recording. I'm always pressing the wrong button.